So one of the things that we need to actually understand, right, is how YOLO works. How many of you actually wondered how this algorithm would work? So this is an exciting lecture where we're gonna try to go through to understand how YOLO works. Yeah, so we're gonna cover quite a bit of stuff. We're gonna cover why computer vision, right? Why it's hard. We're gonna talk about object classification. If you want a lot, you have already done that, right? We're gonna talk about single object detection, right? Which is very different when you have multiple different objects, okay? We're going to talk about sliding window, which is a really interesting approach to solve computer vision problems. Regional CM, faster regional CM, and how they solve the object detection. And then we're going to go to this exciting topic, which is single shot learning, or you only look once, right? Finally, we're going to talk a little bit maybe beyond object detection. If you want to learn more about it, right? What kind of things can we do with it? All right, computer vision, right, is really seeking understanding of the world, and it's very hard. It's very hard. For example, you look at this photo here. There's a lot of information, right? There's a lot of information. You know, why, for example, people in the background, they're laughing. Oh, maybe, oh, this is a special person, right? This is, you know, our favorite president, you know, and maybe what they're wearing. And do you guys know that, you know, once we developed a vision, right, there's exponential kind of like explosion of life on Earth, right? So computer vision, of course, is, you know, vision itself is really, really important. But as I illustrated before, computer vision is very hard. You know, we can perceive, you know, this beautiful picture, but a computer will just see pixels, those numbers. And then when you think about it, the same object, because we're looking at the object differently, it might appear differently. And, you know, for ones who have cats at home, you know, cats can have any shape, right? Can go through any cracks, can be hidden in anywhere, but that's still a cat. Right, that's still a cat. You know, if you have a lighting difference, right, you would have things very different, right? This is the same person. Intra-class variation, these are all dogs, right? I've yet to see in our camp someone, you know, some team wanted to do a dog species classifier. I think that would be pretty interesting. And here we basically like, we have to classify every single object here, right? Every single dog here as a dog, right? Intra-class variation is huge. What about occlusion? Where the kids hiding everywhere, right? In this case, did you guys even notice there's a kid here? I don't know how this kid was be able to hide in here. That's some remarkable kind of achievement right here. What's really, really interesting is in the last few years, right? So you guys are really a lucky generation. You know, in the basically prior to 2012, the computer vision is basically, you know, use traditional computer vision methods. And what we're looking at here, right, is basically the mean average precision. Basically, the larger this number is, the more precise, the more accurate these object detection algorithms. But what we can see here is that prior to 2012, you know, before the deep convolutional neural networks are used, right, we can barely go to 40%. And now, right after 2012, when we have a famous neural network called AlexNet came out, and then we can see the average precision, right, is increasing really steadily over time. And now, you know, the precision for, you know, this 20 categories of things we're going to detect is more than 95%, more than 95%. So basically, you know, using deep convolutional nets, this problem has already been solved. So what's deep convolutional nets? The thing we're going to talk about first is basically the thing that we, you know, sort of like have done that before, right, which is image classification. That is, we only need to know, right? We only need to know that what is in this picture. What is in this picture? And there's only one thing in this picture, right? Sort of like what we have done in the handwriting digit format, right? Where we're trying to guess in that single image, is that 1, is that 2, is that 3? And we know there's only one single digit. So you have definitely seen this before. You have this 28 by 28 pixel, and then use filters, right? 10 filters. As I said, these filters, they're trying to extract different features and map into this image. You can look at here, which is basically one filter doing work, right? 5 by 5 kernel. And you're moving one by one, one by one, one by one, right? And then you have the 24 by 24 pixel component. And then you do the max for it, and you get to 12 by 12. Can someone tell me why you go from 24 by 24, go to 12 by 12?
The stride is 2.
That's right. because the stride is 2, right? At 24 by 24, each time stride equal 2. Therefore, it's 24 divided by 2 is 12. And then, as I said, this is one kind of like unit. You have the com layer, and then you do the max pulling, right? And you got to here, and then we do it again. And at the end, you can see here, this is 28 by 28. You go to all the way to only 4 by 4 now, right? 4 by 4 now. The only thing that's increased is maybe the number of layers. So this is 28 by 28, which is almost like 900 pixels. And here you go for like, 16 times, 20, right? Which is, 320. So then what you're going to do is basically you flatten it out. You basically take all these guys, and you flatten it out, and you have the fully connected layer, and then you have the output here. And the output have 10 neurons because we have 10 digits we need to classify. So once again, extract features, and then combining these features to use it for different things. So here are various tasks of computer vision. We have already seen the classification case, but you can combine classification with localization, meaning that in this single image, we have one object, right? We need not only classify what this object is, but we also need to know where that is. And then the object detection is the one that we're interested to understand how it works. In this case, right, there are multiple objects of different categories. And not only we have to classify them, we also have to know where they are. So this is classification plus localization. This is called object detection. And then the semantic segmentation is really, you don't look at the objects, you just look at pixels, right? You look at each pixel, what classes do they define? Do they belong to? So, this simple image here, right? So we have basically, we can classify, these pixels that belong to grass, these yellow ones that belong to a cat, this is belong to a sky, this belongs to the tree line. And then the holy grail of computer vision, right? This is called instant segmentation. It has a very high order. That is for every single pixel, right? We need to assign that to a class. So today we're not going to talk about these two. We're only going to focus on those two. So as I said, classification, you have already seen that. You have already been able to classify a handwritten digit to be a digit. And then the localization is something, where we have to also output a bounding box. You guys have already been an expert in terms of processing these bounding boxes, right? X and Y, W and H, right? They're essentially specifying, where is the top and left for this box, and then how wide it is, and how tall that is. Evaluation-wise, classification, we use accuracy. Anybody remember what accuracy is?
The percentage of what you got right over the total.
Exactly, right? The percentage of what you got right, divided by the total. Yes, great job. And then for the localization, the evaluation is IOU. Do you guys know what IOU is?
Isn't that intersection?
That's right, intersection over union. So you look at two boxes, this would be like, maybe the true, where the cat is, right, the truth. And then maybe a prediction would be something like this, okay? That would be a pretty horrible, prediction. But then the intersection, right, would be, this part. The union would be, all the areas surrounded by the box. So if IOU equal to, 95, right, 95%, that means a pretty good IOU number. Okay, so classification, localization, how can we achieve that? Well, we can just turn that localization problem to be a regression problem. And what do I mean by that? Well, right, we already know that basically we need a whole bunch of these filters and stuff, right? Max pooling, convolutional neural network. We can use that to extract classes, right? And here are the fully connected layer. What if we just do the same thing? We add another, pipes, just like what we had before, except, when you look at the classification problem, we basically have, come out with class scores. Maybe cat is 0.9, dog is 0.05, and car is 0.01. And then we define a loss. Loss is essentially you compare the corrected label with your predicted label. You take that loss, and then what you do is you basically say, you know what, we're just going to do the same for the localization, because at the end, you're just trying to come up with 4 numbers, right? So what we're going to do is we're just going to basically say, all right, we're going to compare these 4 numbers with the corrected, or the true boxes. And then we're going to come up with a loss. And we're going to train this neural network by combining these losses together. Okay, so that's classification plus localization, right? You're basically penalize the network if you do not get the classes right. And you would also penalize the network if you do not get the coordinates right. That's pretty simple, right? You see how our understanding build upon each other. Okay, so L2 loss and softmax loss, these are the things that, talked about here. I won't go into details about them, but if you're interested in learning more about the softmax loss and L2 loss, you can come back to this slide and really understand what they are. And if you don't understand what they are, I'm pretty sure there are resources out there, online can explain those things in much more detail. But all you need to remember at this point is basically you're combining the classification loss and the localization loss together, right, to train the network so that the network would be able to predict the right object at the right location. So what about detecting multiple objects, right? How can we do that? So let's look at this problem here, right? So we have this, busy, street, probably in Brazil or I don't know, Europe or somewhere. But the problem is that we want to find all the people in this picture, right? All the people. Now you can see here, this is a pretty daunting task because, you have people like different sizes, right? Like, this gentleman here, you have people, sort of like far out of the screen, right? This woman here, you have people who are like, there's a person here, right? That's occluded. How can you find all these people? How can you do that? Given what you learned, you know already, right? You know already. If you have a picture that has a single object in it, you can use localization plus classification, right? You'll be able to detect one person. Given what you learned, how would you solve this problem? Okay, well, so here's a thought. What if we use a sliding window approach? So we basically have this window here. For every single window, we do that classification and localization algorithm. And we move it around a little bit, and then we do the calculation again, right? So basically you're sliding all the window all the way, and anytime you detect something, you report it. But then, how would you solve the problem where these people are different sizes, right? So then what you can do is maybe you can shrink the image, right? So in this case, like you basically, or relatively, you change the size of the sliding window, right? So that you can predict better and better. Can someone tell me what's the problem with this approach? Do you think this is a good approach?
It might take a long time, and then you don't know exactly what size to shrink or increase the sliding part to.
That's exactly right. Right? This seems like a pretty brutal force kind of approach, right? That is, as you said, it can be really, really expensive and you don't know what to do with it. That's exactly right. So this approach is actually never used in practice, right? Because it's very, very expensive. When you start sliding, you have the many, many windows of different sizes. You have to extract many different extractions, and you have to do many times, right? Classification and localizations. So sliding window, pretty bad approach. So what can we do? Well, so, this is 2000, fast forward a few years, right? 2013 now, right? End of 2013, beginning of 2014. Then we come with this algorithm called regional proposal plus CNN. And the way that we did it is basically you take this input image, right? And then you basically would apply traditional computer vision on top of it. You're basically asking the question, how can we just use the raw pixels values, say, oh, like all these pixels around it, they have the similar values, we're just going to classify them as one region, like examples like that. You basically first extract the region proposals. You propose inside that box, there is basically one object. And typically you would extract about 2,000 of these regions. And then what you do, right, you can see this warped region. You put this into, fix this into this box. And now you guys recognize everything here, right? Which is basically you do the ComNet and then you do the fully connected network, and then you'll be able to classify these different regions. Can someone tell me why we need to, warp these pictures into this small box? Why do we need to change the dimension here and always fix the input of these neural networks to be a fixated dimension?
Is it because when you're doing like convolutions, it has to be a square?
No, it doesn't have to be a square, because all the networks, right, they're defined in a certain fashion, right? They would require the input image to be a certain dimension. And you don't care the aspect ratio, what or not. You basically just wanted to, use this image and put in this machinery, but this machinery would require a fixated size for these input images. So you basically just warp them together and use this as inputs. The problem here, right? The problem or the highlight here is that step 2 here, this is not trained. This is not trained at all. Right? This is using some traditional computer vision techniques. That's the main point. Now, the problem of RCN is that it just takes too long, right? It's very slow. The training takes about 84 hours, right? That's a long time. And then the prediction, it takes about 30 seconds per image. Can someone tell me if each prediction is going to take 30 seconds per image? Why would that be a problem?
Well, if there are a lot of images, then that's going to be a lot of time.
What about for self-driving cars? Each prediction takes 30 seconds. I mean, 30 seconds you can travel, I don't know, like half a mile. So it would be like only half a mile later, you can take another image and maybe do another prediction. Do you think that kind of self-driving cars, would you get on top of it? Would you be in that? It's like, I'm just gonna look at my phone for 29 seconds before I look at the road, and then I can make an adjustment, right? That would be horrible. That'd be horrible. So speed is definitely something we need to do better. Okay, the same author come with this paper called Fast RCN. And the way they do it is very interesting. One of the most interesting things, right, prior to Fast RCN is you take one image. For every single image, you have to extract features. You have to do the ConvNet, max pooling, whatnot. And you have to do that 2,000 times. And when you look at what's actually very time consuming is the part where you have to put the whole picture into a neural network and extract those features. So what if we do it the other way around? That is, we take this picture, right? We take this big picture and we first extract those features, right? We use the ConvNet, extract those features. And so we condense this whole thing, right, into a much smaller dimensional space. And then what we do is use traditional machine learning on these guys, right, on these guys. And then, you guys recognize this? This is basically Softmax to do the classification. And here is to do basically the localization problem, right? So the key insight here is instead of you do 2,000 convolutional neural network and do the feature extraction and whatnot, you do only one time. And the results are dramatic. When you look at the RCM, the training time takes about 84 hours. The fast RCM, quite acceptable now, right? It's about 8 hours. So this is certainly, fixating on one kind of like training problem with the same training data. And when you look at the test time, right, in terms of seconds, the RCN, if you just focus on the blue bar right now, RCN, as I said, is more than like 30 seconds. For this particular example, it's like 49 seconds. That's horrible. But then for the RCN, it takes only about 2.3 seconds, right? 2.3 seconds. So we're talking about 20-fold of increase in terms of speed. And funny enough, when you look at the red bar here, the red bar is basically you exclude the original proposals, right? Exclude the original proposals. So this is the time where the neural network has to spend time to do interesting stuff. And you can see here for the fast RCN, the neural network only spend 0.32 seconds. As a matter of fact, the majority of the time for the RCN is actually spent on the traditional machine learning algorithms to do the original proposals on the feature maps. So the results is drastically faster, okay, for the fast RCN.